So today we have another mixed spectroscopic techniques question, and the clues we have today are a little different from what we usually get. So we've got information on mass spectroscopy, NMR, but no infrared this time. Instead, we are given the empirical formula data, which can be used to work out the molecular formula. So just like I've explained in my previous videos, the idea is to put those clues together like pieces of a jigsaw and work out the identity of the organic molecule. Normally, we would start with the infrared spectroscopy information because it's very easy to identify the functional groups that are present in the molecule from the IR stretches. But we don't have that today. So instead, we're going to be getting all of our information from the proton NMR and the other clues we've been given. So the first thing I'm going to start with is the empirical formula data, so we can turn that into a molecular formula, and that will be our starting point. So with that said, let's get into it. So the way we work out empirical formula is we just calculate the basic ratio of each atom. So carbon, hydrogen, oxygen, and the percentages you treat as being the same as the mass in grams. And then what we can do is we can work out the moles of each element, divide through by the smallest number, and then that will give us the empirical formula. So let's go ahead and do that. So moles will be 54.54 over 12 for carbon. Then for hydrogen, 9.1 over 1, because the atomic mass of hydrogen is 1. Then for oxygen will be 36.36 divided by 16. So putting that into the calculator gives me, for carbon, 4.545. Then for oxygen will be 2.2725. And then for hydrogen, 9.1 divided by 1 is obviously just 9.1. So there's our ratio. There's our numbers that we're going to put into a ratio, rather. So this, and this. The next thing to do now is to divide through by the smallest number, which we can see is the oxygen. So 2.27525 divided by itself is just going to be 1. Then 9.1 divided by that gives approximately 4. And then 4.545 divided by that number is approximately 2. So therefore our empirical formula is C2H4O. And let's call the empirical formula EF. But that's the empirical formula. What we need is the molecular formula so we can see the actual number of carbons, hydrogens and oxygens in the molecule, which we will then use alongside the NMR to identify the different hydrogen environments. So how can I get the molecular formula from the empirical formula data? Well, for that, I'm going to use the mass spectroscopy information provided, which is this, just highlighted in blue there. So mass spectroscopy produces a graph where it shows the different abundances of each fragment that makes up a molecule. But the very last peak in the mass spectrum is the mass of the actual molecule, known as the molecular ion peak, which I'm just underlining there. And that gives the mass of the whole molecule, which in this case we can see is 132. So the relationship between the empirical formula and the molecular formula is this. The molecular formula is the actual number of atoms of each type in the molecule. The empirical formula is the simplest building block, if you like, that is used to assemble the molecular formula. So the simplest whole number ratio of atoms. And the relationship is if you divide the molecular formula, which is what I'm writing here, let's call it MF, by the empirical formula, let's call it EF, you get a whole number. And the whole number, 2, 3, 5, whatever it is that number you multiply the empirical formula by. So let me just go back to the empirical formula there. You multiply these numbers I'm highlighted in green by this whole number, and that will create the molecular formula. So let's have a look at what the empirical formula actually comes to. So we have 2 times 12, which is 2 carbons, plus 4, plus 16, 1 oxygen, gives us a total of 44. And then the molecular formula, the MF, well, that's given to us. It's right there. It's 132. So 132 divided by 44 gives us exactly 3. So I need to multiply this number by 3, this number by 3, and this number by 3 to create the molecular formula. And that gives us C6H12O3. So the molecular formula we're working with today has 6 carbons, 12 hydrogens, and 3 oxygens. So now that I have that, I can see what other clues I'm given to work out the identity of the molecule. And the next thing I need to turn to is the NMR. Okay, so if you look at the NMR spectrum, we are given just 3 peaks. It shows 3 peaks. And in my previous video, I describe the basic rules of NMR for both proton and carbon NMR in how to interpret the spectra, which I'm going to briefly recap now. So rules, NMR, and number 1, the number of distinct peaks. So what is a distinct peak? Let me just show you what that is. This is equal to the number of hydrogen environments. Number 2, the area under the peak, which is referred to as the integration. That's a word that comes from maths, by the way. So when you integrate a curve, it's the area under a curve. And that piece of information tells us the number of hydrogens in that environment. So when you see a number above a peak, like this, that tells me there is 1 hydrogen in that particular environment. And then finally, number 3, the greater the electronegativity of an environment, that is equal to or produces a greater chemical shift, which is the delta value on the y-axis. So for example, if you have a hydrogen attached to a carbon and that is immediately next to, say, an oxygen or a fluorine or a nitrogen, which are electronegative atoms, that will cause the chemical shift to increase and produce a greater chemical shift. So it's a really useful clue to watch out for, because very common is you have the same functional group in the molecule, or the same group like a CH3 or a C2H5, but they may be in different locations along the molecule where the electronegativity is different. So you end up having basically the same environment on the NMR graph in different places. So now that we know those rules, let's take a look at our NMR. And we've only got 3 peaks, but there's something else they've told us. So use another clue. So if I just highlight this pink there, it tells us that the NMR spectrum has been carried out in D2O, which is heavy water, deuterium oxide. So D stands for hydrogen with a extra neutron. So it has a proton and a neutron. And what it does is it specifically targets certain groups, OH groups, NH groups, and removes those peaks from the NMR graph to simplify it. So before we actually dive into this spectra, I'm just going to add a note on that. So function/purpose of D2O. So you know this going forward, should you see it again, you understand what it's about, why we use it. So number 1 is it removes OH peaks. So think alcohol, think carboxylic acid. And then number 2, it removes NH peaks. So think an amino group or anything which has an NH2. So those protons that would have produced a peak in the NMR, they just simply disappear. So that's what's happened there. So that is telling me that there is more peaks for this NMR graph that have been removed. So let's look to see if we have any other clues. So it says a scientist is researching compounds that might be suitable as fuel additives. So we've used the empirical formula to generate the molecular formula. We've used this bit of information. And now we have this at the bottom, which I'm going to highlight in yellow. When the spectrum is run without detour, there's our clue. There are two additional peaks with the same relative peak areas at 11 and 3.6. So that is telling me we have, for our molecule, I'll just write it over here, we have a total number of hydrogen environments equal to 5, because 2 of them have been removed. There's only 3 remaining. And the environment with the chemical shift of 11 is going to be, well, this is where we turn to the datasheet. So by the way, just before we go any further, if you want to use the exact numbers from the datasheet for NMR I am using, it is attached in the description below. So if you look at the datasheet, the functional group that is around 11 is a carboxylic acid. So we know for a fact that the chemical shift of 11 is the carboxylic acid functional group. Because if you look at our molecular formula, we've got 3 oxygens to use up, and 2 of them have already been used in that functional group. So that's great. And then the second one is at 3.6. So if you look at the datasheet for 3.6, we can see that, well, there's a few options there. So let's take a look. So the way to work out what this functional group could be is by a process of elimination. So immediately I can see there's a hydrogen attached to a carbon to a nitrogen. Well, there's no nitrogen in this molecule, so it's definitely not going to be that. So that's out. Then we have the hydrogen attached to a carbon on a benzene ring. Well, there's no benzene ring in this molecule because benzene has a chemical shift at around 7, and that's missing from this spectrum, so it's definitely not that. So that leaves either a hydrogen attached to a carbon with an OH, which is this one, or a hydrogen attached to a carbon which has a C double bond O. And we don't know yet which one of this is going to be, so that's what's in my mind for the chemical shift of between 3 to 4, and they've quoted it as 3.6. So that's what's in my mind. And that then would provide the third oxygen, so to make up the molecular formula. So let's dig a bit deeper. Right, the next thing that catches my attention is this. So if you zoom in, we can see that that is split into 4. 1, 2, 3, 4. And by the way, when you look at NMR spectra, every little blip, if you like, every little spike counts as something you have to read. So that there, that is a quartet. And that quartet has an integration value of 1. There's just 1 hydrogen in that environment which is split into 4 quartet, which means it must be next to a carbon which has 3 hydrogens on it. So according to the n+1 rule, I'm assuming you know what that means. So n is the number of hydrogens on the adjacent carbon next to the environment we're considering. So n equals 3. So 3 plus 1 makes 4. So that would make a quartet. So that means we can have this sort of piece somewhere where we have, that's the hydrogen, that one there is that one there, and it must be attached to a carbon which has 3 hydrogens like so to create that quartet. So that piece of the jigsaw then is going to be in the molecule somewhere. Okay, so we're beginning to build a picture now of what's going on. Remember what I said at the start of the video? You look at the clues from each bit of spectroscopy data. You treat them as pieces of a jigsaw. You put those pieces of the jigsaw on the page, and only at the end you assemble them to create what you think the molecule is going to look like. So let's go ahead and do that. So far we have C double bond O. That's one jigsaw piece. We have this somewhere. How do I know that's there? Because the hydrogen must be next to a carbon with 3 hydrogens to create a quartet. 3 plus 1 is 4. Also, with that consideration, this CH3 is opposite this hydrogen, which would mean the number of hydrogens adjacent is 1. So 1 plus 1 would make 2. And for that one, it would create a doublet. So for this CH3, there would be a doublet corresponding to this hydrogen. Well, do we have a doublet there? Let's check. Yes, we do. So that's reassuring. So there's a doublet there, and look, it has an integration of 3, which means there's 3 hydrogens in that doublet environment. And if we go back, there's the 3 hydrogens. So this is looking good so far. So we have 3 environments already sorted. The quartet, the doublet, and then this one, well, that's been removed from D2O. So now let's turn our attention to this, our final peak, which is a sharp singlet at about 1.4, 1.3, 1.4. Now that is saying there is 6 hydrogens in that environment. Now if you ask yourself, how can you have 6 hydrogens in an environment when carbon can only form 4 covalent bonds? That's impossible. Well, actually, this is a really nice big clue as to something that happens in molecules all of the time, which is when we have symmetry, or the same functional group or the same part happening at the same time. So obviously carbon can't form 6 bonds. So why does it have an integration of 6? So when this happens, that is always the same thing, which is, I'm just going to draw it down here, a carbon bonded to 2 CH3 groups. Because 2 CH3 groups will be identical because they're attached to the same carbon. So the integration covers these 3 hydrogens and these 3 hydrogens at the same time. So it gives an integration of 6H. And whilst we're at it, even though it's not in this question, sometimes you see an even sharper peak which has an integration of 9. So 9H would correspond to 3 CH3s attached. And actually, when this clue is given in a question, it's something you want to happen because it gives away the molecule, and a lot of the molecule as well, because we're using up so many carbons here. We've used up 1, 2, 3 from that molecular formula. So now let's take a look at our next jigsaw piece to put down, which was the carbon attached to 2 CH3s. So we have this piece, and this piece. And we check our molecular formula, and it's C6H12O3. And so far, from our jigsaw pieces, we've got 1, 2, 3, 4, 5, 6. So there's the 6 carbons used, which is great. And then we have oxygens. We have 1 there, the other one there, but there's 3. Okay, so where's this other oxygen coming from? How could it be integrated into our pieces there? Well, if you go back to what I said a moment ago, we've got this environment at about 3.6, and we can see the one of 3.6, which is mentioned there. It doesn't tell us whether it's a singlet or a doublet or anything like that. It just tells us there's an environment of 3.6. So the only thing that it could be is this thing I've drawn here, the C double bond O, that chemical shift would be more to the left, as in a chemical shift of 9 or 10 or 11. If it was an aldehyde or a ketone or a carboxylic acid, well, it can't be any of those because we know it's a carboxylic acid, so that's out. So therefore it must be this one, which is a carbon attached to an OH. And that OH fits perfectly within that range. So we've got to find a way of putting on an OH bond, which is responsible for that 3.6 chemical shift value, into one of our pieces. So let's look at this one. It can't go on that one because it's already a functional group. This one, you're the CH and the CH3, that's already been discussed. That's what's generated the quartet and the doublet. But then we have this one here, which is the carbon attached to 2 CH3s on the right. And there's a spare space there, so we could try it there. And then we're going to put these pieces together. Now, I will say this at this point. These questions can be very difficult, and there will be a certain degree of trial and error. And that's okay. That's the whole point. You put these jigsaw pieces down on the page. You try and assemble them to make something that fits. You look at your drawing. Then you circle the environments in your drawing and attempt to match them to the spectra that's been provided. And if it fits, then you know then for a fact you've got it right. So let's put this information together. So we have OH, C double bond O. We have that bonded to the CH and the CH3. And then this carbon bonded to an OH, CH3, CH3. So something that looks like that. So what I'm going to do next is let's clean up this graph, put the molecule next to it, and then assign each of those environments to check that I've got it right. Okay, so here's the cleaned up graph and the molecule right next to it. So let's recircle our environments. So we had the carboxylic acid group, we had the CH, we had the CH3, we had the OH, and then we had the CH3 there. And we know that this environment is not going to be present because of the D2O, and neither is this. So now we can go ahead and assign the remaining ones. Let's just call them A, B, C. So A is going to be the quartet because it is opposite a CH3. So 3 plus 1 makes 4, which is a quartet. And it's going to have an integration of 1 because there's just one hydrogen in that environment. So therefore A must be that environment there. Then B, it is opposite a CH, which has 1 hydrogen. So 1 plus 1 makes 2. So this is going to be the D doublet. And that will have an integration of 3 and a chemical shift of around 1 to 1.5. So the only thing that fits that is this one. And then finally, C is the singlet, which means that it's attached to a carbon which doesn't have any other hydrogens on it. So N would be 0. So 0 plus 1 is 1, so it's a singlet. And the integration for this is 6H because that CH3 is the same as that one. So therefore, this must be C. So what you have is your molecule drawn on the left. You have the labelled NMR graph on the right. So when an examiner looks at this, he knows or she knows that you have deduced the structure of this molecule without guessing, without fluking it, without cheating, that you've done it and you've proven that the way that you've worked it out is by looking at the environments in your molecule, matching them to the NMR. So when you come to describe the process, even if you mess up your explanation and it doesn't sound as good as it should do, if you've got a clear diagram labelled that's cross-referenced to the NMR, you will go in to get full marks, which in this case, well, you can see it's a lot of marks, 6 marks, and they're always this sort of number of marks between 6, sometimes running up to 10. So get your diagram done, label your diagram, match it to the NMR, and you'll be fine. Okay, so that is it for today. Thanks for watching. Please do like the video if you've had any value. It helps the YouTube algorithm. Check out the other videos I've made on this topic. I know it's difficult, but the more practice you have, the better you will get. Thanks for watching and see you in the next one.